All right, everyone, welcome back to our extra hour. I've already mentioned that we're going to work some problems today. We're going to do three problems. They're going to be similar to the homework. They're going to be similar to what's on your exams. And then I'm going to show you a little bit about how to solve differential equations. So the purpose of this is, at this point, I'm kind of getting to know you, looking at your homeworks, and getting a little bit of a better idea of what you do right, what you do wrong. So I thought about some of these questions based on that. I'm also previewing some of the harder things that are coming up. This first example, you're going to notice that you've actually already had it. And then I'm going to go over wave function normalization. We're just going to do some examples. I've noticed that, some of you are going to answer every question correctly, so that's great. So I've noticed that some of you, though, are not figuring out how to use identities correctly. Normalization involves, since you have to integrate this wave function squared to 1, you got to use an identity to do that. So that's an identity example. Now, I also mentioned several times now that we're going to see how you solve a second order differential equation. The Schrodinger equation is a second order differential equation. The value of that is that when you have an exam, where we're at now is we're going to have a lot of make the wave function continuous and smooth at a boundary. Boundary conditions are how you solve these problems. By solve, I mean you solve the wave function. But in almost all the cases, like in the last hour, everything is e to the ikx, or e to the minus ikx. What you're looking to solve is k and a and b and all that. What you don't want to have happen is at the exam, I'm like, here's a potential surface and the wave function is e to the ikx. And you go, what? Why is that? No, we have to be over that part. You have to just look at the e to the ikx and say, well, that's fine. I wonder what k is, right? If you lurch at the first statement, then that's a problem. You want to lurch at the second statement, which is usually what is k, what's a, so that things are smooth and continuous. I don't want you getting cross-eyed at the statement of the problem. It's working the problem that you should have a problem with. And hopefully not. And we're going to do some example problems and you have your homeworks as well, right? And as you know, and you've seen already, I base the exams. They should be fairly similar to the homework, just for the minimum reason that I wrote all of it, right? Okay, so before I turn into a stammering mess, what's coming up soon are we're going to have to start working in spherical coordinates. That's because when we get to atoms are round. You can't describe round things with x, y, and z. So when we run into spherical coordinates, you're going to find that we're going to have operators that look like this. And you may notice this from, I can't remember, second or third homework. This isn't exactly the same problem as on that homework. It may be. I don't quite remember what I've written, and that's just because I've written so many homeworks at this point they get jumbled up. Okay, so again, very similar to a previous homework. Why did I do that? Because when we're on spherical coordinates, this is going to be like d theta, d phi, and you're going to have pretty complicated things like this, and you're going to have a bunch of them. You can't not know how to do this right, because everything from here on out, well, pretty soon we're on spherical. Within a week or two, we're on spherical coordinates, and we're going to stick with them. So you've got to be able to work this correctly, and that's one of the reasons you've already been, you've already had these in front of you already. Let's make sure that we got it down. Now, what goes wrong? And I'm not going to write this down because I don't want to write down what's wrong because you may get confused. What goes wrong is that you start partitioning these up into separate problems. No. Calculus is done from right to left. I don't know. I wonder if that's like because Hebrew is written from right to left. I don't know, but that's how we do it, right? So start here, put a little cross, and then you just go to the left. And by that, I mean you can't just, what goes wrong is you look at that and you make that the number 1. That's like starting a sentence by reading in the middle. No, you don't do that. Now again, it's a little funky that we go from right to left, but anyway, you get the point. You have to take each operation in the order in which it comes, again, from right to left. So, now I will write this down because I'm going to do it correctly. The first thing to do is just write everything down again up until the first operator, and then stop. Okay, sorry. Yeah, first operator. God, see, now I'm confused. The first operator going from right to left, and that's this. Okay, so I've written this down. I just wrote it down without thinking about it. I just wrote it down. Now I'm at technically the first derivative, and now I need to do it. Now I've been doing calc long enough to do product rules in my head. Whatever, you take your time if you need to, but I'm pretty sure I can do this right. Derivative of this, leave that alone, and then vice versa. Derivative of that, leave that alone. And again, I do this all the time, so it's not too hard to do it quickly. Okay. Now you see why you couldn't make this the number one, because you would be done. And that would be nice to be done, because you see what we run into? Again, let's leave the derivative. You see, when you don't wipe this out, you've got product rule to the nth power. Right? This, unfortunately, is much harder than it appears, because now we've got like a bunch of product rules, but it does have the benefit of being done correctly. All right, so what's the last step? Okay, derivative of that, leave that alone. Derivative of that, leave that alone. Leave that alone. Derivative of that. Okay. I hope I did that right. Okay. Derivative of that, leave this alone. Okay, leave this alone. Derivative of that. Okay. I'm going to just pray that that's correct, because otherwise I'm going to be messing around with the digital thing for hours. I think you've probably seen I've made a couple of mistakes and I digitally change things, and trust me, I can lose hours when I do that, so I'm going to hope that this is correct. Anyway, so I'm just going to stop there. Everything else is just kind of a permutation, but again, look out for this when we get to spherical, which again is that's like in 2 weeks. All right, let's see, next deal. Let's normalize some wave functions. Why not? Because you have seen time and time again that we are almost universally going to figure out wave functions not by solving the Schrodinger equation. Wave functions do not come with normalization constants. You have some trickery to figure out a wave function, and then you're going to need to normalize it. And maybe that's just going to be a question on the exam. In fact, I'm certainly going to ask that question on the exam. I would make that kind of an early question, because this really ought to be on the easier side. And if it's not, then we're going to do a problem. All you have to do is use an identity. There's one part you might screw up, so let's hope that you can use identities, and if not, this will help. And then let's see if we can intentionally get stuck in a way that probably will get you, and that way hopefully we won't do it again. All right, anyway, I'm just rambling. So, what I'm going to do, I'm going to do a vibrational wave function. All right, that's coming up soon too. Actually, really soon. I think that's next week. Okay, so this is the ground state. And again, I'll just tell you that this is the wave function. And you should, if I'm doing that, you should say, is that normalized? And I would say no. Okay. 2 alpha squared. My alphas kind of look like 2s. I'm doing my best here, but I can't really help that. And then I will also do the excited state. First excited state of the bond vibration. And that is 2x over alpha. And now I'm exaggerating it too much. Oh, that bothers me. Okay. Anyway, try to just be careful that that's a 2 and that's an alpha. If you get a little confused, that's okay. Because, well, hopefully my writing isn't that bad, but If you have a little trouble now, that's fine. We're not at, this isn't an exam, right? Okay, so let's do this one first. Okay, now, of course, you're going to look at the cheat sheet. You're going to integrate from all limits. That would be from minus infinity to infinity. Again, you do need to know, I probably generally have to tell you what the limits are because particle in a box is 0 to L. But, you know, in almost everything else, it's usually minus infinity to infinity. So, and that's this case. Now, one thing that you can mess up is forgetting that you're trying to make the wave function square and the absolute value of the wave function square. That means complex conjugate times the wave function. That is what you're integrating, and it better equal 1. Now, again, if you're thinking like, oh, how am I going to memorize that? You're not. It's on the cheat sheet, right? So this, again, is strategy. If you're trying to memorize stuff like this, that may come at the expense of everything I'm about to do after, which is the actual problem. So think about that. All right. Now, the problem is that you're not going to get the number 1. That's why we have a problem. You're going to get like the letter A. So let's say that you get something, I'm just going to call it A. Now, how would you make this normalized? If every term was divided by whatever this comes out to be, and it could be complex, you know, it's like pi, or maybe it's pi I, or whatever, it's a half, I don't know. If you divided the wave function, and of course then it's squared, and it could be complex, that's true, then you would definitely have gotten 1. Right? So again, you see exactly what this 1 over the square root of that value is what the normalization constant would be. Okay, whatever. Let's go backward and just integrate what we have, and we'll see what it's equal to. Okay, e to the minus x squared over alpha squared? Yeah, squared. This is why I use the Microsoft Word editor, which does a pretty good job of making things look good. So, you won't like get too cross-eyed trying to read my handwriting. That won't happen at the exam. All right, so what? Okay, you've already done, I threw a problem set at you, I think it was number 3, you've already had that by now, where I asked you the complex conjugate of a sine or a cosine, and of course it doesn't have I in it, so it just doesn't change. And I did that just to mess with you, by the way. But you should know that it doesn't change. Well, in here I don't see the letter I, so the complex conjugate doesn't do anything. Okay, so what do we get? Okay, next up, all right, let's insert the infinity to infinity, and e to the a, e to the b is an identity. You get e to the a plus b. So I'm looking at this, and what I'm seeing is that I get e to the twice of the argument, which means that it's x squared over 2 alpha over alpha squared, not 2 alpha squared, because there's 2 of them. Okay, and now it's a lot less scary. And let's see. All right. Let me go over here. You got it whittled down. You should be able to do this because, look, this is ridiculous. Now look for an identity. You're looking for an identity that has the same limits, and I do that as a guide. Remember that what I write down is what I found off Google, because that's what you're going to find. And you may recall this is a bell-shaped curve. I think we've seen these integrals before. Okay. And now all you have to do is, let me work down here. You've seen this among some others, so be careful. All you got to do is figure out what A is, right? Okay, so you got to map this onto that. Like, just imagine, in your head, imagine you put this like on cellophane, like clear plastic, and you overlaid it, and then you want to overlay, A is what? Well, hopefully you're going to see that A is 1 over alpha squared. Remember, we've been doing this for quite some time now. Okay, with that, you're basically done. What this is square root of pi over 1 over alpha squared. So I would probably, you might want to leave it like that, but that kind of makes me want to throw up a bit. 1 over x is x, so this ends up being pi alpha squared. Now, that's just because I kind of have an overwhelming need to make it look nice. When I know that, my nose tells me it actually looks a little bit nicer than that. Now, if I actually get stuck all the time with 1 over x. Put it in your calculator. 1 over 7. Don't use 1, don't use 2. 1 over 7. Is that 7? It is. All right, so that's how you make sure that you're not doing something unbelievably dumb. Okay, and so, well, that's it, right? You write that down, go on to the next question. You get the exam back, and you got 6 out of 10. What did you do? What did you do wrong? This isn't the answer. You're halfway there, a little over halfway there. Remember that the wave function up here, all right, wave function normalized is going to be the wave function just like you were given. My 2's and alpha, I told you they look terrible. Over the square root of this. Okay, so the God, this is kind of painful, isn't it? So it would be here. Let me simplify that. Okay, so what you would have is let me make sure I'm doing this right. Yeah, pi to the 1/2 alpha to the 1/2. Okay, that looks kind of bad. Of course, I would understand if you get a little bit flummoxed about what's what. But so the lesson here was you managed to integrate this thing. Now remember, the purpose was that you should get 1. You should have gotten 1.0, but you didn't. You got this thing instead. So you have to divide by the square root of that. Right? So that's this. I just neatened it up. Don't do that if you get confused. Square root, right? So, because if you had that here, right, you see why? Because you have 2 of them. So what you would have gotten then is constants remain by 1/2. Now I hate it when you run into mixed symbologies, but square root of pi alpha squared divided by square root of pi alpha is 1. So there you go. Anyway, so I just wanted to walk you through that. Let's do one more. I promised you to do another one, and let's see, I hopefully have that. Now I'm going to do the first excited state, this one here. I shouldn't have written it down. I hope that didn't confuse you. Let's just, I'll work down. Let's do that one. And again, this is just a lesson in identities. That's all I really want to get through. Again, be careful. Complex conjugate times the other thing. Going forward, half the problems are going to have an I in them and about half long. About. Don't hold me to that, but you get the idea. Sometimes it's going to matter, sometimes it's not. And it's kind of random how the letter I shows up. It's really kind of wacky. I don't feel like there's any kind of pattern to when wave functions have I in them, but you are going to see it quite a bit. Okay, so if you recall what the first excited state wave function is, I don't think you can see it, so sorry about that, but just trust me that this is it. So it looks pretty similar to the last one, but now you got an X in front of it. Okay, as usual, let me take all of the constants out. Don't forget them, because usually when you do that, often the constants, there's a bombastically large number of them. Not so much, I guess, in this case, but that's usually the case. There's usually a lot of constants. And when they're out, all of a sudden this looks way easier. All right, identity, right? Then you see, write it down, clean it up, identity, and then we're not one step away, but two. You see, this is why I'm going to make this problem an early problem on the next test, because it really is routine at this point, right? I hope so. It ought to be. Now, what's sucky about this one is this is one of the ones that has kind of a bit more of a complicated. We ran into some of these when we were doing Maxwell-Boltzmann. I hate it when it's like kind of complicated like that, but anyway. That's just because I like to simplify it for these examples. You don't need to do that, you know that. Okay, mapping this to that. Again, the only thing you have to do is identify A. Okay, looking at that, I can see A is 1 over alpha squared, the same thing it was last time. Therefore, this is, don't forget the constants. They didn't go away. Half, okay, square root of pi. Okay, 1 over alpha is alpha. Okay, but it's alpha squared, but cubed, so it's alpha to the 6. Okay. Now let's clean that up a bit. So 2, 2 alpha squared. Alpha cubed, square root of pi. This is a bit of a nightmare. No, that's not actually, wait a minute. Look at this. That's actually not bad at all. Okay, let me double check. Is that right? Yeah, that's right. Okay. I freak out sometimes. Okay, so you put that down. You can say it's normalized. And you got a 60 again. Write out the wave function. Right? It is, again, I know you can't see it. Let's write out the normalization constant, which is the square root of all that. 1 over the square root of all that, 2 alpha, pi to the 1/2. And I know I'm mixing up my symbologies. And then write down 2x over alpha e to the minus x squared over, and I'm just writing all this down again, so there you go. All right, again, just another example. Oh, it's not very, kind of hard to see what's what. Anyway, a little messy, sorry. But there you go. So again, I promise I'll have an exam like a question like this on the exam, and you see that don't be memorizing complex conjugate times wave function when it's on the cheat sheet. Just remember to do this part. Just get it to looking like the identity which you locate. As in Maxwell-Boltzmann, you just have to make the thing work. And then write down the answer. Hopefully you remember that you got to make the normalization work. One other thing, and I'm not going to write this down, but one of the other common mistakes I see is that someone will write this down and then they'll try to apply the limits, like this is the answer to an indefinite integral, and then you apply the limits. No, and here's how you don't. And notice I'm not writing that down. I don't want you to get confused. How do you know not to do that? Because where would you put the infinity, right? This is the answer. The limits have been applied. And even if you were inclined to insert the limits, where would you insert them? There's no x, right? Remember, the way that you would do this is that some math genius knows what the indefinite integral is, and then when you do infinity minus infinity, this is what is left over. That's why this is the answer. Again, a common mistake, so don't do that. Okay, one last example, and I guess we'll end decently early, but it's an extra hour. A lot of faculty cancel these throughout the semester, and obviously I'm not going to do that, but you guys are paying me. You do need to give me just a few minutes to wipe out the board, and we're going to do that last bit, and we'll call it an early day. Okay, last bit. How to solve a differential equation. So I'm actually going to solve two, oh, what the heck? This is a new pen. I just bought this pen, so that's funny. Hopefully it just needs to wake up or something. All right. Got some setbacks every now and then. I think this pen, yeah, okay, that's a little bit better than those pens old. Hopefully it'll limp through this last bit. Okay, so what I'm going to do is for V is, so for constant potentials, that would include the free wave where V is 0, 0 is a constant, or any of these more recent examples we've been doing, where for any given region the potential energy is flat. The answer is always e to the ikx plus v e to the minus ikx. And that is what I'm going to show you, how exactly that comes about. All right, and so again, v could be 0. Irregardless, we have some constants that mathematicians don't care about. Double derivative. So that's why this is a second order differential equation, because there's a double derivative with a function equal to itself. And remember, I've just done a little bit of algebra, v naught, whatever. It's a constant. Just don't forget that. When we do things like solve more complex problems where the potential is not constant, I'm often just going to tell you, like, a mathematician solved this way back when, and here's the answer. That's just because this isn't really DiffyQ class, right? Okay, so next step, we're going to take all the constants, and in this case, we can put them all together. You just don't want to forget what they are. And in this case, k squared, there's our k is always showing up in our answers for free wave, and for the examples we just did. Can't ever get away from. Remember on the, God, what is it? Second or third lecture? No, the first week of quantum, I mentioned k was 2 pi over the de Broglie wavelength, and I'm like, you want to remember that because you're going to see it again. So, okay, now when I do that, what I then have is I can say that here's our double derivative, and it's equal to minus k squared. Wave function. Now mathematicians like to put it this way. I like sometimes to work problems, and what I've done here is I'm bringing everything over to the right. I have to admit, I kind of like this a little bit better, because you know what I get out of it is I see that these cancel each other to equal 0. Here, I see something that's really confusing. The double derivative is equal to something times the thing again, and I'm like, all right. But when I see this, I see this is going to wipe that out, and so that's like a lot easier. And I can see like e to the k, right? A double derivative is going to bring down a k squared. So I'm already kind of able to figure out what the answer is. Okay, now tell you what. Before we do this is a second order differential equation. Let's solve the first order differential equation first. Now, for one, so that you get a better idea of what's going on, and number two, actually I need to use it in the solution to this one. So I kind of bait and switched on you. Okay, what is a first order differential equation? I should have written that down. That's second order. A first order, okay, it would be, it's easier, right? So instead of a double derivative, I've got a single derivative. And let's not get our constants too confused. This is a different problem, so I'm going to use a different constant. I don't want to use a k squared there, because that's like for a different problem. And that could actually lead to some confusion. So this looks like the same as what I wrote there, again, because I'm using a different letter for the constant because it's a different problem. But for the most part, it looks the same, except that's a single derivative, so this should be easier, which is correct. Now, I'm actually going to unfold this. I'm going to put this back the way it used to look for a very good reason. I'm bringing the deal back over. And the reason is that now what I'm going to do is I'm going to divide. I'm going to divide by the wave function, so I'll write that here. Okay, what you got is okay, so I just, derivative of wave function with respect to x, so there's the derivative of the wave function. I brought this guy over to the left. And where's my partial of x? How about I'll just bring that over here. Remember, you can juggle these. You should have seen that last semester. You definitely should have seen it, maybe you don't remember. But when you have, you can treat the a, change in a, change in b is equal to 1. Therefore, change in a is equal to the change in b. You can basically treat them like they're algebraic variables. Okay, now again, Calc 1, you have seen this. This is the change in the natural log of the wave function. You should have seen that. And this is whatever that is, so now let's integrate them. Now again, I've already said that c is a constant. Let's say that, let's not presume that. What we can then do is, I see that what we're going to get is natural log. When you integrate a partial, you just get the thing back, right? Natural log of the wave function. And let's just, I'll leave it like this. And now I know that the wave function is just e the minus c times the integral of dx. Which of course, now I'm assuming that c is a constant. I didn't want to, well, let me not generalize it. You see what I mean? Now, if c is a constant, then you have, then that would be the case. So again, I left it like this because maybe that's not a constant. Maybe that's a function of x. Okay, so again, I just wanted to walk you through how you solve the first order differential equation, but let's go back to our Schrodinger equation. What do we do here? Okay, so I'm going to need to work another board. This is going to be a little strange because I'm going to do something that's not quite related to solving it. So this is going to just seem a little bit odd at first. So it's like I'm going to solve it by doing two separate derivations. That's actually very accurate. But that sounds weird. I know that sounds weird, but it'll make sense at the very end when basically I'm going to put these two together. So with that said, let me just actually start doing it. Okay, what do I want to do? So looking at, let me write it down again. Let me write it down again on a fresh board. And then what I'm going to do is I'm going to write something that kind of looks like a quadratic equation. Okay, now here's my first step. It's like I'm using an identity. So I'm going to write something that's related. I'm going to write A, double derivative, plus B, single derivative, plus a constant. All of that's going to work on the wave function. It's going to give 0. So you see I've written like a very generic form. This is very specific. That's the Schrodinger equation. And I've made a very generic form of that. Now what I'm going to do is I'm going to define. Now again, this is going to seem really weird. It turns out you can define alpha beta as C over A and alpha plus beta as B over C. Now that allows you to solve what alpha and beta are, but hopefully you're like, well, wait, why do I care about alpha beta? Let me show you. Because when you do that, you can now do this. Derivative of x, wave function x, plus alpha wave function x. And now for beta, derivative of the wave function plus beta wave function is all equal to 0. Okay, now if this times that is 0, you can imagine that each term needs to be 0. So this has got to be 0, and this has got to be 0. Okay, well this looks just like that, right? Those are just two first-order differential equations. Those are two first-order differential equations, and that's the answer. Okay, so what this proves is that the wave function is going to look like e to a constant. Now I'm going to use the letter r, x. Okay, now you may notice that I didn't write this down. I've written something else down. I said this would be a little strange and it'll all make sense at the very end. Kind of like The Witcher. Does anyone watch? Anyway. At the very end, it all made sense, but okay. Here's what I'm going to do with this. Now, this is not part of the solution, kind of. This was to show you what I'm going to try to see what the wave function looks like. Now I'm going to actually try to solve it, and I'm going to solve it with this. And you're going to see why I use the letter R. Okay, let's go back here. Let's go back here. And I'm going to put that in e to the rx times the wave function. So I've got a double derivative e to the rx, and where am I at? Plus b single derivative e to the rx plus c e to the rx is equal to 0. Okay, nothing is more simple than the derivative of an exponential. So what do we get? We get, I'm going to factor it, e to the rx, a r squared, double derivative of e to the rx is r squared e to the rx, plus br plus c is equal to 0. Okay, now here's why I used the letter r. This is not 0. That's a function. How can a function be 0? You may be thinking, oh, plug in 0 for x. Well, e to the 0 is 1, so you failed. And that's not really, the whole thing needs to be 0. Okay, with that said, this is not going to be 0, but this can be 0. How do you make something squared plus something quadratic? Recognize this? This is a quadratic equation. Recognize that? It's a quadratic equation. What are the answers to the quadratic equation? The roots are, now you see why I use the letter R? The answer to this equation is to find R, and it's just the roots of the quadratic equation. Of course, we know what that is. Now, we'll have two of them, right? It's quadratic, it has two solutions. It's going to be minus b. Now, I have this memorized because, 4th grade happened. And sometimes I have to double check myself. So minus b plus or minus b squared minus blah blah. Okay. Now we have to, so it's kind of like an identity. So now I have to map this onto that, and to do so, I see that specific to our Schrodinger equation. You may notice that this term doesn't exist. That means that b is 0 for our specific problem. A is 1, and c is k squared. Okay, and that means that r plus or minus is plus or minus square root of minus 4k squared. A is 1, so that's divided by 2, which is plus or minus ik. There you go. All right, looks familiar because remember that the wave function, I'm not using the board too well, remember that the wave function is actually, the solution is actually e to the rx, so that's e to the plus or minus ik, right? There you go, e to the ik, or e to the minus ik. It's always the answer. Now let me throw a little math theorem at you. So you probably don't know this. I'm sure you don't know this. We have two answers, e to the ikx and e to the, yeah, did I write that? Anyway, we have e to the ikx and e to the minus ikx. So it turns out that there's a theorem of differential equations, which is that, now let's say that there's some kind of constant times the function. What the theorem says is that you can make a linear combination, that means just add them. You can make linear combinations of the solutions, and that is a solution. So e to the ikx, e to the minus ikx were solutions, so I can add them together, and you still have a solution. I multiply them by a and b because I'm not sure what the normalizations are or what their relationship is. And you run into exactly the freaking thing I've been repeating for a month now to the point you're sick of it. A, e to the ikx plus b, e to the minus ikx. All right. Hopefully mission accomplished. Remember, part of my goal was to get you sick of seeing this so that when you have to figure out k or what a and b are, that this part doesn't get you cross-eyed. Because if that gets you cross-eyed, you can't even start answering the question. That, and you've also learned a little Diffie cube. Remember, that's a good thing. You may hate it, but if you are good at this, or at least you can do it, I don't know, more money? All right, so now I'm rambling. It's like midnight anyway. So we're ending a tiny bit early, and I hope this was useful. And have a good weekend. I will see you all on Monday.